All right, so let's see what you need to know for your Unit 2 exam. Not so surprising, in Chapter 5, we talked a lot about these different forms of electromagnetic radiation. You're going to want to know the order of these cousins: gamma rays, X-rays, ultraviolet, visible, infrared, and radio. And as I've listed them, we're going from the highest energy to the lowest energy. And then also, as they're listed here, we're going from the shortest wavelength to the longest wavelength. And last but not least, as they're listed here, we go from the highest frequency to the lowest frequency. So you're going to want to know that. Frequency is the number of cycles that pass a single point in 1 second. And wavelength is actually a distance from a repeating unit. It's a distance of completing one wave. You're going to want to be able to draw the general structure of an atom. Of course, and I don't have it here, but I'll go ahead and add it. In the center, we have the nucleus. This is the nucleus. And you're going to want to know that there are protons and neutrons. And then outside here is what? These are the electrons. So kind of be able to know the general structure of an atom. And there are different things that can happen with electromagnetic radiation. One of them is scattering. And so there's a question on there about why do we see things, and we see things because light is scattered off that object. Specifically, the color we see it is the color that is scattered, and all other colors are absorbed. Okay, the three types of spectra we have the continuous, we have the absorption lines, or bright line spectra. We have the continuous is the first one there, and the other one that has the dark lines is called the dark line spectrum or absorption spectrum, and the last one is the bright line or emission spectra. And actually that kind of goes with the next one. Electrons are creating these different spectra. And specifically, the dark lines are created. Remember when I stepped down off the chair? Wait, no, I'm saying that wrong. The dark lines are created as I step on the chair. Basically, I'm sucking energy, and that energy that I need to step onto the chair is like electrons going from a lower energy to a higher energy state, and they need energy to do that, so they're sucking energy. So that makes the dark lines. The bright lines were like when I stepped off the chair, when I stepped down to a lower level, I was actually emitting light. Those are bright line spectra. Okay. Two types of telescopes. We have the reflector telescope that uses mirrors, and the refractor telescope uses lenses. I guess one more thing back to the previous one up here that creates the lines. When I was stepping down or stepping up, that was a specific energy. So it's not just any random energy. It's a specific energy. Okay, two types of telescopes. Last one actually has to do with telescopes too. Whether it uses mirrors, a reflector, or uses lenses, a refractor, what happens is the telescope lens will bring light to what we call a focal point. That is the ant-killing region. That's where all the light is concentrated. On to, I guess there's another one down there. There's a couple of them. So the Doppler effect is actually very helpful with regard to stars. And here's the deal. If a star is moving away from us, kind of like you see that left guy is actually has the light moving away from that left guy, then actually the wavelength that that star is sending out is going to be lengthened, and we call that a redshift. If the star is moving towards us, like you see the guy on the right, then actually the wavelengths are going to get shorter, and it's going to be a blue shift. The last one, why would we want to put a telescope in outer space? And actually there's at least three reasons. One is to avoid light pollution. So we're talking about like the Hubble Space Telescope. The next one listed here is to avoid turbulence. Like the reason things twinkle is because we kind of have different temperatures of air moving and the air is what we say the light is refracted as it passes through the Earth's atmosphere. And then the last one is that the Earth's atmosphere actually blocks some energies that penetrate it. So if we get beyond the Earth's atmosphere, then we don't have them deleting that information. Okay, on to the next chapter. This was the chapter on the formation of our solar system. So you're going to want to generally know the term solar nebula basically was that cloud that ultimately turned into our sun and the planets. The next term up there says system of moons forming around Jovian planets. And remember that all the Jovian planets, all the gaseous planets, have moons. And if we look at Jupiter and Saturn, they have a crazy system of moons especially. So it's kind of thought, just as the planets accreted, remember the term accretion is actually how the planet kind of snowballs. So also kind of around the gaseous planets had their little mini disk where moons formed in orbit around the planets. Let's see, anomalies of our solar system to be explained. So actually there are three. One is Earth's very large moon. The other one is Venus rotates backwards. And kind of related to Venus is Uranus rotates on its side as it orbits the sun. And all three of these can be explained. I kind of have here in orange. All three of these can be explained by simply recognizing that early on in the formation of our solar system, there was all sorts of kind of random things, and they got smacked. The Earth got smacked to create the moon. Venus got smacked to go upside down. Uranus got smacked to lay on its side. You're going to want to be able to list out the two types of planets, the terrestrial planets and the Jovian planets. Here in green, I've also gone ahead and put the planets in order. You're going to want to know the planets in order. So, of course, it's Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. So, differences between them, the terrestrial ones are rocky and they have metals. The Jovian ones are gaseous. They have a rocky core, a small rocky core compared to the rest of their volume. And then here in blue, I say that terrestrial Earth just has one large, weird, anomalously large moon. And remember, Mars just has kind of like two potato-shaped moons. But if we go and look at what the Jovian planets have going on for them, all of them have moons and all of them have rings. How did Earth get its water? Well, we think that actually it was imported from, like beyond Neptune, from the Oort cloud or the Kuiper belt in the form of comets, and Earth was struck by comets and kept its water. The term accretion is kind of that snowballing, the kind of building up of a planet over time. Let's see, frost line. Frost line, remember, is kind of the mark between the terrestrial planets and the Jovian planets. And then the last one here, the kind of glowing thing in the middle would be the sun. The purple thing around the middle would be like Neptune. And then we have, actually beyond Neptune, we have the Kuiper belt. And then kind of in a spherical shape around our whole solar system, we have the Oort cloud. So the Oort cloud is farther than the Kuiper belt. Earth plate tectonics, that's kind of as the Earth's crust, actually lithosphere, is broken up into slabs and it moves around on liquid mantle underneath it. The next term, crust, mantle, lithosphere, outer and inner core. So crust, these are kind of listed from outermost to innermost. So of course you know what lithosphere, remember, is made up of the crust and the top part of the mantle. Now the core actually has two things going on. The core is where the metals end up, but it has a solid part in the center, and it has kind of has, I feel like an amniotic fluid, kind of like a baby in a womb. So it has the solid inner core and then a liquid outer core. Okay, planetary differentiation. That was actually as heavy things sink to the center of the planet. And I kind of liken that to if you have Italian salad dressing, if you shake it up and if you let it set down, if you let it set, then your more dense liquid is going to sink. Surface erosions come in two forms on Earth. That would be the wind and the water erosion. And as they do their thing, wind and water actually then resurface the Earth. Mercury's cliffs, otherwise known as scarps, were thought to have formed as the cute little planet cooled. Caloris Basin is found on Mercury, and it's a kind of a neat feature, and actually it's kind of jumbled on the opposite side as the Caloris Basin on Mercury. Valles Marineris, that's on Mars. That's that large canyon. Venus has those thick clouds but we have a kind of a map of Venus, and we got the map by putting a satellite in orbit and then using radar to kind of ping down, hit the planet, and then to map it like that. Greenhouse gases generally warm a planet. How did Mars lose its greenhouse gases? How did Mars lose its atmosphere? And it actually has to do with its size. It cooled down more quickly, and as it cooled down, it solidified, and it can no longer support a magnetosphere. And so as it lost its magnetosphere, then its atmosphere became vulnerable to the sun's solar winds, so it's kind of blown downstream. But Mars, speaking of Mars, Mars actually has evidence of past flowing water. Phobos and Deimos are the two potato-looking the two potato-looking moons that orbit Mars. Mars actually is a red color due to rust or iron oxide. And the magnetosphere, requirements in order for a moon or a planet to have this protective magnetic field is that it needs to be spinning, and it needs to have liquid in its center. And so I have check marks here. The first M stands for Mercury, then Venus, then Earth, then Mars. And I have an X over Mercury as it has cooled and does not have a magnetic field. Venus has an X also. It's actually, we think, geologically active, but it rotates so slowly that it doesn't have a magnetic field. Earth has a great magnetic field, and Mars has a little bit of a magnetic field. And then we go on to our last chapter on the Jovian planets. So one of the things you're going to want to know is that we talked about how Jupiter actually is more dense than Saturn. Jupiter's volume isn't all that much larger, but it's a lot more massive. So what happens is kind of with these pillows that with Jupiter getting one more pillow, it actually made that, if you can see there on the right, the bottom pillow is flattened more with the addition of the other planet, of the other pillow. Let's see. So then I have what drives Io's volcanic activity, and I put tidal flexing, and I didn't bring in all the figure, but remember we talked about Io actually is the closest of the 4 Galilean moons, and the other Galilean moons actually kind of make it flex out when they are passing Io. So, and I kind of put up here, it's like that stress ball getting heated, tidal flexing. Saturn's rings are actually, they're not solid, they're chunks, and they're very reflective, so actually it's chunky icy material. And the thing that makes the two outermost planets blue is the presence of methane in their clouds. Triton actually is one of the moons that orbits Neptune, and it kind of has this sort of cantaloupe sort of texture to it. The 4 Galilean moons are listed here in order of closest to Jupiter going outward. So we have Io, Europa, Ganymede, and Callisto, and they all orbit Jupiter.